record. And one more thing to do, and one more thing to do, and yes, yay, finally. It's only week 8, the end of week 8, and I finally did it. I set it up all with even 30 seconds to spare or something. Yay! Okay, so goal for the term, at least one of them ticked off. So, what a happy thing. And what a happy thing to see all of you. Well, now when I say all of you, there aren't so many of you. Hey, Xiaoyan, lovely to see you too. Oh, sorry? Oh, yes. Oh, thank you very much, Luke. Oh, damn it. Oh, okay, I actually did, but I should have more. It's early in the morning. I woke up thinking, oh, lecture's at 12, plenty of time. And then half an hour later, oh, lecture's not at 12. Oh, damn. But a little bit of adrenaline helps too. And how are you all here this beautiful? Oh, thank you very much. That's really good to see, because it is week 8, the end of week 8. And although things are not necessarily as hectic as they have been or will be, it is getting late in the term, and I wouldn't be surprised if some of you are feeling a little bit tired by now, and possibly also a little bit stressed about upcoming events in the exam and stuff like that. But yeah, I hope you're all doing well, and do let me know if you are struggling a bit or falling behind or any other thing. Just want to have a chat, and please let me know, and I'll do what I can. And I really would like you to support each other as well. You've done so beautifully on Piazza, and keep up that awesome work. Yeah, what about you? Do you have anything to say or ask about or anything before we get? No? Cool. We're looking at chapter 5 here, which is this big chapter on number theory and algebra, but it's not nearly big enough to encapture half of the stuff that I might like to stop and look at more carefully, and some of you might already appreciate. It's some beautiful stuff that we've been looking at, and it's also really useful too. The modular arithmetic material that we've gone through, I hope that most of you understand sort of what's going on. We'll need it in chapters, well, the rest of the chapter, but also in chapter 6 and 7. And what we're looking at now, and what we began to look at on Tuesday, was the concept of a field. So some of the typical fields are these down there, the rationals, rational numbers, complex numbers, real numbers, and so forth. But the particular fields that you've seen in this course are the ones Z2 and Z3. They're just the binary numbers, ternary numbers. In other words, they're very, very finite. They're not like infinitely big like the real numbers or the rationals or whatever. They're very finite, and that's a really good thing because, for instance, if you think back to chapter 2, then we had error correcting codes, and code words. And we didn't have infinitely many of those code words. We just had, you can write them down, like here are 4, here are 16, here are, whatever. So we want a small number of code words, and that makes things nice and manageable. But for that, we typically need some finite fields. And sometimes we need small finite fields, and sometimes we need big finite fields. But we need finite fields. So that's what this part of the chapter is about. And just saying, what's a finite field? And we had that terrible, scary slide there with all of those properties. And it's sort of fascinating to know that, like right now, what we can do is, since we've been, in kindergarten, addition, subtraction, multiplication, and division, that sort of stuff there. That's all we need to do. And, in the usual way, if you add 2 plus 3, it doesn't matter whether you do it in this order or have them swapped around, 3 plus 2. But that's something that we have to check. That's a property that we have to check. And actually, if you think about it, that's something that we have to learn when we're like, 2 years old or whatever. It's, you take these two blocks here and 3 blocks there, or, little chocolates or whatever you want. And if you swap them around, you still get 5. And that's not a trivial property to learn. But of course, it's trivial to us because we're so used to it. But each of these properties is not necessarily trivial. But of course, we think they are. So for technical purposes, there's a lot to say. But we're not going to say it because this is not really about algebra and number theory. Hey, but in the back of your mind, you can say, okay, that's all the stuff that we can sort of assume and know. But from an intuitional level, a field is just what we're used to from the real numbers and the rational numbers and so forth. It's a bunch of numbers, whatever they might look like actual numbers, integers or real numbers, or something a bit more weird like we've got to. But it's stuff that we can add, subtract, multiply, and divide whenever we're talking about something non-zero. So the only thing that we can't divide by non-zero. And that leads us to what actually is a finite field in the very simplest case. And we saw this, we've talked a little bit about this. If you take all the integers, divide by some number p, and look at the remainders, then you get a small set of numbers, 0, 1, up to p minus 1. Those numbers form a finite field if and only if, well, one of the properties is valid. If you look at all of those properties, all of them will be true, except possibly the existence of inverse, this one here. Not every number necessarily has an inverse, as we've talked about, but if p is prime, well, then every number has an inverse. It's invertible, so that axiom is ticked off as well, and therefore that set is a field. So this is the very simplest type of finite field that we have. But it turns out when we see the big picture, the final answer to what is a finite field and how to how to describe them, well, it's actually just that theorem there, with a bit of extra complications. We're taking copies of, for instance, ZP, if P is prime, some number of copies, let's say n copies, and then you see those numbers, instead of just one number, we've got a vector of numbers, and then we can do vector operations with addition and subtraction and scaling, but we can also multiply these vectors because when we're going to express those vectors in terms of polynomials. So the coefficients of the vector, we're just going to place as the coefficients of polynomials. Yeah, Luke, yeah. I think that's sort of almost given by definition, because when we are dealing with a finite field, almost always, it's because we've constructed it or explicitly said, here's a field that's finite or something like that. Sometimes we might get into the situation, on rare occasion, in theoretical purposes at least, pretty much never in practical purposes as far as I can think of at least, where we'd stumble across a field. Oh, here's a field. Yeah, oh, look at that pretty field. And hey, field, are you finite or are you infinite? And it might be sometimes that we could raise that question, but the question almost never comes up because we've almost always got that information from the beginning. Yeah, thanks a lot. Any other questions so far? Or any comments? Cool. A polynomial, well, you know what a polynomial is, but that's the generalization of the numbers that we're going to look at. So if you just have one number, like for instance the constant term here, a0, well, you could generalize that to say, well, that is a tiny little polynomial, sure. And what about bigger polynomials? Well, there you get a generalization of numbers, and that's exactly what we're looking at. But we're going to be looking at things in different ways. So you can look at this polynomial as a vector, or as a polynomial, or just as one object. They call it f. Like it's a number in itself. It's sort of like a complicated number, but it is nevertheless some sort of number. So that's the way that we're thinking, and there are various ways of thinking also, apart from those three ways there. Anyway, you've got this wondrous property. Hey, when we generalize from the integers to these bigger numbers, like polynomials with the coefficients being in some field, then almost everything still holds that we're looking at and seeing held for integers. For instance, the division algorithm still works, or the division theorem. If you take two polynomials and divide one by the other, then you get a unique quotient, and you also get a unique remainder. And what does that mean? Well, the remainder is something smaller than what you're dividing with. That's less than or equal, bigger or equal to 0. Well, what do we mean by big now? Because now we're dealing with polynomials, not real numbers or whatever. Well, big here we're measuring in terms of the degree. So if the degree of a polynomial that you get when you divide as many times as possible is smaller than what you're dividing with, that's how we measure size. It's a slightly rougher measure than our usual integer. You know, you're going along the number line, and at some point, well, actually, if you're looking at me, I should be going this way to the right. But nevertheless, if we look at size in terms of divisibility and other properties like that, then actually this is perfectly suitable for the task. It's a good way of seeing it. It's a good measure of size, and it makes everything work. So we've got the division algorithm, and we've got the, although I have to say the division itself is a little bit more painful than normal division, when you're doing it by hand at least. But we've also got the well, things like the remainder theorem. Actually, that in itself was not something that we get from integers. Well, we do implicitly, but this is something that we get beyond integers, that when we've generalized integers to the polynomials, we have new and exciting things to say. So this is one of them. And from the remainder theorem, we want to get to the factor theorem. We got to that as well, just one step from the remainder theorem. And this one was important. Again, this is high school stuff that you've seen, possibly primary school, I don't know, depending on your primary school. But yeah, it just says that if you have a root of a polynomial that corresponds to the linear term x minus c, that's got to be a factor of the polynomial, and conversely. But here we've proved it very quickly. Okay, that introduces the notion of roots, and that'll become very important for when we look at how to describe and construct finite fields. Anyway, what else? We have one of the last definitions we're looking at on Tuesday was the notion of irreducibility. So, and I told you that you've been lied to most of your life. When someone said a prime number is something that's only divisible by 1 in itself, well, that was not actually the definition of primality, that was the definition of irreducibility. So here's the definition again, just for the broader context of polynomials rather than integers. A polynomial over some field, in other words, with the coefficients being in some field, f, is irreducible if it can't be divided by any smaller polynomial, so to speak. So it's got no proper factors of positive degree. That's just an awkward way of saying we can't factorize it into smaller polynomials. Okay, great. So now it turns out, we're not going to prove it, we're not even going to state it, but it turns out, miraculously, once again, that polynomials, even though they're more complicated numbers than just the integers, they also have the property that what you think of as prime, the word prime, and irreducible mean the same thing. There's a technical definition of what prime is, what a number has to satisfy in order to be prime, and you can use that definition for polynomials as well. But it turns out for both integers and for these polynomials with coefficients over a field, that those two different technical conditions converge and become the same thing. All the numbers that are irreducible are also prime, and all the prime numbers are also irreducible. But you can go to, and here's, I haven't checked this, so this is a bit dangerous to state, especially because some of you might say, oh, that's wrong. You might be able to remember a little bit, but if you take the integers and add and subtract, multiply and divide, whatever you want to do with them, together with something like, now this is probably a bad choice, square root of 12. But anyway, I'm just going to say it anyway, with a little, so if you take those integers, for instance, I think they are not necessarily, then I think the prime elements are not irreducible, or was it the other way around? But in other words, you don't have to go far away from the normal integers in order to find numbers that don't satisfy that prime numbers and irreducible numbers collapse and become the same. Now I'm going to delete that very quickly because that's square root of 12. I don't know whether 12 will work, but you can find small numbers that will make this work. And I also can't remember, by the way, whether irreducibility and primality are completely independent or whether one is a subset of the other or whatever. But I should be able to remember it because I used to teach that sort of stuff back in the beautiful 3521 algebraic techniques and number theory, but that was so long ago. It was a lovely course. Anyway, we have the unique factorization theorem, which you've known forever for integers, but miraculously, again, it's true for the more general setting of polynomials. So whenever you have a polynomial, you can factorize it uniquely into smaller factors. Okay, maybe not completely uniquely because you can change the order of the factors and then you can scale the factors up and down. Okay, great. But apart from that, it's unique. And in the same way that integers can be factorized uniquely into prime numbers, okay, apart from the order and apart from putting pluses, plus 1 or minus 1 in front of each of the terms. Okay, so that leads us to where we got to on Tuesday. And what are we having a look at now? Well, the next thing to look at is a greatest common divisor. So we're following very much in line with what we're looking at when we're dealing with modular arithmetic for integers. The next thing here is a greatest common divisor, a GCD, of two polynomials. And, well, that's just it's a greatest common divisor, so it's a common divisor, some polynomial that divides both f and g. And it's greatest in the sense that, well, here we could have chosen the degree as the greatest, but it's more useful to say, well, it's that technical condition that we had for integers again, where we're saying it's the greatest common divisor if all of the other common divisors divide it. And that's an equivalent statement, but it turns out to be a more useful statement if you're actually dealing with proofs and stuff. Now, one tiny little word that you might notice is a greatest common divisor. It's not the greatest common divisor. And I'll show you quickly sort of what that means just in terms of normal numbers. So if we look at the GCD of 10 and 24, what numbers divide 10 and 24? There's 1 and 2, nothing bigger than that. But wait a second, there's also -1 and -2. So the biggest number in terms of divisibility here isn't just 2. You could also say, it's -2 and 2. So each of those numbers we could consider them to be greatest common divisors under this divisibility property. But of course, with integers, it's really easy to say, oh, forget about the minus. We'll stick with the positives. And then you say, oh, okay, cool. That makes everything easier because then we've just got one number and it's a function. It's the GCD of those two numbers spits out some number, and that's easy. But here with the polynomials, it's not so easy because we can't just say, oh, it's the positive polynomial, because what does that mean? Especially if we're dealing with coefficients over a field where there is no positive or negative. You can always put a positive or negative, but there's no linear order to these things. So what we do here is we choose a representative. And in fact, that's what we do here too. Out of these two, we say it's got to be the positive one. And that's the same sort of thinking that we're going to do here. We're going to say, well, the monic one. It turns out that all of the greatest common divisors of f and g are actually pretty much the same thing. You can get every one of them by taking one of them and scaling up and down by any scalar, any number in the field there that you've got. So we can just scale any of these greatest common divisors down to have that the leading term is 1, and that's the greatest common divisor that we'll use to represent the other ones. So that's the greatest common divisor there. It's monic. So it's a technical condition that's a little bit annoying, but it's not a bad and it's not too annoying. So it's okay for our purposes. But sometimes people say, oh, I don't like that monic stuff, and it's breaking the symmetry. I had all these greatest common divisors. Why do I have to just choose one of them? That's unfair. What about all the other? Now they feel excluded. And then you can say, okay, let's be inclusive and talk about the greatest common divisor, not as a single representative, but as the whole set of greatest common divisors. And sometimes people do that too. But anyway, here. So an example here would be x cubed and x to the power 4 minus x squared. And if you look at those two polynomials and think, what polynomial could divide both of them? Well, then we quickly see, well, what about x squared? That divides both f and g. And can we get any bigger polynomial? In other words, a polynomial with greater degree? No. Okay. Well, then, in fact, this is our greatest common divisor, and we check that it's monic. Yep, there's a little invisible 1 in front. Great. It's the greatest common divisor. Awesome. Now, of course, in this case, there is only one greatest common divisor because the coefficients that we're dealing with are binary, zeros and ones. So we can only scale by something non-zero. But if we change this question a little bit to have that it was in Z3, so now we've got the numbers 0, 1, and 2 that we could scale with, and we can't scale with 0, then we could scale by 2. So a greatest common divisor could look like this, 2x squared. That would be a greatest common divisor, but it's not the greatest common divisor because it's not monic. The 2 there, if we scale it down to 1, then that's the greatest common divisor. Does that all make sort of sense? Great. It's, on the one hand, it's simple stuff. On the other, it's a little bit weird that we have to look at the greatest common divisor in such detail when such an sort of for everyday purposes with integers, such an intuitive and normal thing. Okay, now that we have the greatest common divisor, then we can go on to the next step, which, just like for integers, is looking at how do we find it. And again, beautifully, everything works in the same way. We can use the Euclidean algorithm to very, very quickly in logarithmic time just to keep dividing remainders into remainders until we get 0, and that'll give us our greatest common divisor. But even more, if you apply that algorithm backwards to what you get using the extended Euclidean algorithm, as we've seen for the integers, we can get what Bezout's property, or Bezout's theorem, lemma, whatever you want to call it, it gives us the very last line that the greatest common divisor can be expressed in terms of the original polynomials, f and g, times some a and b, where a and b are polynomials themselves. Everything that works for integers still works here, which is, again, maybe not so surprising because we're just taking a number of copies of these integers, but at the same time, it does get more complicated, so it is sort of miraculous as well. So anyway, let's try to find the GCD of these two polynomials. We've got f has degree 4, g has degree 2, so f is bigger, and let's go. So f divided by g, okay, damn it. Now, I won't say that this is fun. That would be a lie. Unless you're different from me and you find it fun, in which case, yay, awesome. But I don't want to, assume that you might find this boring, but I don't want to prejudice you and say that it's, boring if you might have assumed. What am I going on about? I'm very bad at multitasking. So here I'm trying to concentrate on getting the numbers right. Yep. So now I said, okay, I'm dividing by this. How do I get rid of the top term? Well, I take the top term there and I could divide by x squared. Okay, great. That if I multiply all of this g here by x squared, then I hopefully have got the right thing there. And please do check, especially because I am a little bit tired. So if we subtract, we get some cancellations going. And please do check that I've got everything right there. Now we've got x squared, and then we say, okay, great. Are we done? No, because that remainder x squared is just as big as what we're dividing with, this polynomial here, because they both have degree 2. Okay, I must continue. So if I subtract one lot of this, so x squared plus 2x plus 1, and then subtract that, then I get minus 2x minus 1. And by the way, there's one little number to note here. What numbers are we dealing with? Well, we're dealing with the ternary numbers. So I could also say that this is equal to, instead of minus 2, I could call it plus 1. So that's x, and instead of having minus 1, I could say plus 2, or I could just leave it as minus 1, but that's the remainder anyway. So the quotient, this would be the quotient, this would be the remainder, and there we go. And so, okay, x2 there, plus x2. Do you have any questions about this process there? This is just the way that I do it. You might do it in some other way. If you haven't done this before, you might find a completely new way of doing it. It doesn't matter which way you do it, as long as it suits you and, well, you get the right answer, I suppose. But do you have any small questions about any of the details here, or any large questions about the small details? No? Cool. So that was the first step of the Euclidean algorithm, and then you sigh, okay. But it's not too bad because the polynomials get smaller. So what we do is we take these two polynomials and we divide them into each other. So there we go. And if you do that, and now I'm not going to do it, but you get x and 1 and the remainder 1, well, that's as small as it can get. Now if we divide these two, x plus 2 divided by 1, well, we can always divide by 1, so we get 0 in remainder, so we don't have to do that. But that means that 1 is the very last non-zero remainder. Therefore, it is the greatest common divisor. Yay! And actually, we did have to check one little thing. Is it monic? Well, 1 is very monic. So yes, it's not like a 2. If it were 2, we'd have to scale it. But it's a 1 already, so it's monic. So yay, great. Okay, but we could also express that polynomial, apparently, that little tiny little 1 polynomial, as a linear combination of f and g. And let's do that. So now we go backwards using first this equation there. So 1 is equal to the left-hand side minus this stuff there. And now we can say, okay, we've used that equation. Now we can look at x plus 2 and use the first equation up there and substitute x plus 2, substitute that by f minus this stuff there. And then we tidy up. How many g's do we have? We've got 1g minus this many g's. So that's times x. You've got to remember to multiply by x. So that gives us something there if you tidy it up. And how many f's do we have? We have minus x f's. And there you go. There's our linear combination. And everything works in the same way, as you can see, for the integers or for the polynomials here as for integers. The calculations are just a little bit more messy and slightly annoying, I have to say. The only thing here to pay attention to is that especially for me, I keep getting the pluses and minuses wrong. I always make some little mistake and then have to say, well, that doesn't make sense. So yeah, be careful with that. Also, multiplying into brackets, sometimes I'd forget to do that. But I mean, tiny little annoying details like that are the only thing that's hard about it. Conceptually, it's straightforward and easy, and of course, extremely efficient. All of this is in logarithmic time. Yeah.
If we were going to use movers at the end, could we not factorize our polynomials into the
Yeah.
factors and then see if they have any common factors?
Definitely. Yeah, exactly right. Just like for integers, if you have polynomials that you can factorize, then we can find the GCD and, of course, the lowest common multiple by just saying, okay, which factors do you have in common? Okay, gather around all of the factors that you have in common. Okay, over there, multiply together. That's the GCD, and similarly for the least common multiple. So you can do that, but in general, factorization is difficult. So we usually choose that path. But of course, sometimes we do have the factors, in which case, of course, we don't have to do all of this stuff there. Really good comment. Yeah, Ken.
Yes, it is.
Ah, sorry, thanks. Apparently, I didn't, sorry, I was a bit distracted. Sorry, what was the question again? Ah, yeah. Actually, yeah. Thank you both for your questions. That's really good. Actually, here we do have a case where we can say, see that f is clearly divisible by x squared. So we can actually do a bit of factorization to begin with. Then we can say, and g is not can't be factorized by sorry. Oh yeah. Oh, even better. Oh, lovely. Actually, I might just point that out. Yeah. Oh, lovely. Yeah. Actually, this is equal to x plus 1 squared. So we actually can factorize this really quickly. And actually, if you're doing this by pen and paper, this would actually be quite feasible and not a bad idea to do. And this is equal to x squared times x squared plus 2x plus 2. And damn. And you can see that the difference between them, actually, if we use the Euclidean algorithm on those two, then that'll just in one step give us 1. And you can also say, well, of course, they are co-prime because they only differ by just that constant term. So there's got to be no, there can't be any bigger factors between them. And we can ignore x squared here because x squared doesn't divide, not even, x divides the g. So yeah, you can use a beautiful, thank you both, a beautiful bit of heuristics there to cut down the work. And actually, that's a really good idea if you can. Yeah. Yeah. Yeah, exactly. Actually, and thank you for pointing out or highlighting the notion of irreducibility here. In fact, that'll become central very, very soon in what we're talking about. Yeah. So, yeah, and actually, that's all of these comments are really good because we do have the Euclidean algorithm, and it always works, and it's efficient. But for small examples, it's maybe not always most efficient. Sometimes you can use heuristics like you're doing and just see, oh, we can factorize, or we can sort of partially factorize, and using a little bit of intuition and practice, you can build up, sort of a, you can practice at getting quicker and better at this sort of stuff without just going to use the Euclidean algorithm, just like you would just for small numbers. Like if you look at the GCD of 10 and 24, you don't say, oh, I've got the Euclidean algorithm. Yes, you do, but you can just see from the numbers that the GCD is 2. Yeah, awesome. Yes, here, the next line is a little bit silly, but it's just a point. Oh, thanks, Gary. What does, lovely question. Actually, this ties in with the very next comment here, so beautiful segue here. The influence of Z3, well, there are two answers, at least two answers, many answers probably, but one of them is that we can change how these things look. So instead of having minus x, we could write plus 2x, so 2x, and we could change those numbers a little bit. When you're doing it by hand, that might make some of the calculations just a little bit tidier and nicer to work with. But also it means that because Z3 is a small field, unlike the rationals, or the real numbers or whatever, we don't have to deal with fractions, which is beautiful. So if you're dealing with binary numbers or ternary numbers or other small fields, then the calculations are a lot simpler when you're doing this. Because, well, with binary numbers, whenever you have two terms that are the same, they cancel out when you add or subtract them. And with the ternary numbers, they almost cancel out, but there's a cancellation half the time and so forth and so on. So Z3 has a strong influence on it being easier to do, but also another answer is that, well, when we are looking at a polynomial of that, like this, x squared plus 2x plus 1, if we're told that it's ternary, then it might factorize in one particular way. If we're told that it's, well, actually, that's a bad example. It'll always factorize as x plus 1 squared. But let's look at this one, for instance. This polynomial f here, does it factorize, or how does it factorize? Well, that actually does depend on what field we're dealing with. If, for instance, this were a binary polynomial, well, those 2's would disappear, and we just have x to the power of 4. Here in the ternary case, they don't disappear, so it factorizes in a different way. So it depends on which field we're dealing with, what factorization properties, and therefore, yeah, divisibility properties and so forth. Really lovely question, Gary, and thanks for that. I hope it made sense, and if it didn't, please ask more. Yes, so anyway, we can use the Euclidean algorithm forwards and backwards, just like we did for integers, and there you go. So this leads us to the first part of the answer. What are the finite fields? How can we characterize them? And then we'll also say, well, what can we say about them? And what's the full story? And then afterwards, how can we actually construct them? If you want a finite field of some sort of size or with some sort of properties. So the first thing to say here is, well, if we, we're going to do the same sort of thing as we did for modular arithmetic. We're going to choose some polynomial, and then we're going to divide by it and look at the remainders and look at them modular that polynomial. So just in the same way as for integers. So first of all, we define here the multiples of m. They are with these angled brackets. So m generates that set. So those angled brackets say generate. Here, generation is just you look at all the multiples. So if we have all of the polynomials there, so a here is a polynomial. This is just all the polynomials with coefficients in ZP, or the integers mod p. And so you take all of them and you multiply onto m. So they are all the multiples of m. Well, that's that set there. Now, this notation here, we'll see quite a lot. And it looks a bit scary, possibly, but let's see what it says. So this here, ZP bracket x, hey there, hey. Well, that's just a set of remainders that we get when we take all the polynomials that we've got here and divide by m. And just to give you the integer analog, or rather the special case for integers, when we look at the integers mod m here, Zm, what we're really doing, if you wanted to say it this way, is factorize out by the multiples of m. So this notation here, which we've got up here, is the same as saying this. So you could really, if we wanted to be really awkward about it, say the set of polynomials mod m, we could also write as zp m, sorry, x. X is a, and then subscript m. But we don't write that. That's a bit messy. So instead we use this notation there. But it's the same sort of ideas as we have for the integers here. You take all the numbers that you have. Previously it was integers. Now it's these polynomials. And you divide out by some fixed number m. Previously, m was an integer, now it's a polynomial. And you look at the remainders. And that's the thing that we're looking at here. That's this scary stuff, scary-looking stuff there. But that's all we're doing. It's sort of relatively tangible. I might actually just see whether I can. No, I don't want to. What am I doing? Here we go. Yeah, this comment might be useful for anyone looking at the slides. Yeah. Very, very good question. What degree of n to use? It depends on your purpose. So it turns out that we can use these polynomials to construct fields. So, and then the question becomes, how big do we want our field to be, or what sort of field do we want? Yeah, really beautiful question. And actually, that's something that we actually will need when we're designing fields, and we will design fields, especially in chapter 6, in fact. Yeah, beautiful question. First of all, let's have a couple of quick observations about this set here. Well, it's what this set here is all of the remainders you get when you divide by this polynomial m, which has degree m. So again, when we're taking all of the polynomials that we can think of with coefficients in ZP, and we look at the remainders, well, they're going to be all of the polynomials that are smaller than m. And small, what did that mean? Well, that meant that the degree of whatever we have, the remainders there, are smaller than m, and m has degree n, so it's all the polynomials of degree up to n. And all of those polynomials in the sets, yeah, because if you take any of those smaller polynomials and divide by m, then they will be their own remainder, because they're already smaller than what we're dividing with. So every one of those polynomials of degree up to n minus 1 will be in this set. In fact, that set is just the set of all of those polynomials there. And so how many are there? Well, how many coefficients are there? We've got b n minus 1 all the way down to b1 and b0. And for each of those coefficients, well, we can choose any element in ZP, and we've got p choices for each of those coefficients. So we'll have, well, p to the power of n different choices of coefficients. So that's how many things we've got. And if you want to think of these polynomials in terms of vectors, just take the coefficients. So you could say this is sort of equivalent to these vectors here, b1, bn minus 1 down to b1, b0, and so forth. Then this is really isomorphic in terms of addition and subtraction, scalar multiplication, just to what you get if you have zp to the power of n, n copies of zp. But there is more to the story, though, because we're not only going to go, add and subtract and do scalar multiplication. Now that we've got polynomials rather than written up in vector form, we can do multiplication. We can multiply polynomials, and sometimes we can even divide by polynomials. So, and that's exactly what we're going to do next. Yeah. Yeah. If we have that all of the coefficients b0, b1, etc., all the way up to bn minus 1 are 0, that is one of the elements here, but it's going to be the 0 element of the set. And if it turns out that this set here, sort of preempting things a little bit here, if this turns out to be a field, then the 0 element in the field is exactly just going to be 0, where all of the coefficients are 0. And but we need to if we okay, I'll getting excited already about the bigger picture. I'll go back to the main narrative to not confuse things. Yeah, thanks for that. Yeah. So if we, for instance, look at Z3, the ternary numbers. So we've got here that p is equal to 3, and whoops, that was the ugliest arrow I've seen in a long while. Here we go. And we've got that the polynomial that we choose for some reason, x squared plus 2x plus 1, whatever. Here we've got that n is equal to 2. Well, if we divide all the ternary polynomials by that particular polynomial, then we're going to get all the polynomials that are smaller than this polynomial. In other words, have smaller degree. In other words, they're the polynomials that look like this. They just have degree up to 1. So all of the linear polynomials, or the constant polynomials, or whatever. How many are there? Well, you can count them. You can actually just write them down. Like you've got the 0, x plus 0, which is 0, 0x plus 1, which is 1, and so forth and so on. You've got x plus 2, and you've got a bunch of other ones, but you've only got 9 of them because you've got 2 choices for these 2 coefficients, a and b. Sorry, what am I saying? You've got 2 coefficients. We've got 3 choices, sorry. 3 choices for both a and b, because we're dealing with the ternary numbers here. So 3 choices for a, that's 3 times 3 choices for b, that's 9. That's how many different polynomials we have. And there we go. So far, are there any questions about this? I'm going through it slightly quickly, partly because I want to get through a fair bit today, but also because we've got a lot of tiny little details which on their own aren't too bad, but there is a lot of sort of information overload for those of you who haven't seen this before. Cool, awesome. You're looking happy. There's a happy silence. I take that for understanding. Okay, so now we can do stuff on the set. So we can do arithmetic, addition, subtraction, multiplication, and possibly division. But let's just deal with the first easy three, addition, subtraction, and multiplication. So we've actually got two moduli, or moduluses if you want to, going on. We've got the Z3 modulus, where we're just looking at the coefficients mod 3, take our mod 3 glasses on. We've also got the other modulus, where we're taking whole polynomials and dividing by this polynomial there. So that's sort of like I've got two complicated looking glasses on, and now I'm looking at things, and that's you'd think that that would be more complicated, and it is, but it also makes things very, very simple, as we'll see when we do arithmetic here, for instance. So let's take these two polynomials here. They are in the set that we're looking at. These two little remainders, 2x plus 2 plus 2x plus 1. You add them together. There's nothing complicated about that. That's 4x plus 3. But now we can use the fact that we're dealing with numbers, or the coefficients there, in Z3. So 4 is the same as 1, and 3 is the same as 0. So we have 1x plus 0, really, or you just want to write x. So yay! So we've got two polynomials of degree 1, like two linear polynomials. We add them together and get something smaller. Okay, great. And in fact, whenever you're going to add or subtract any of these numbers together, they form a linear vector space if that makes you, if that means something to you. If it doesn't, well, just take those two, or just take any two elements of that set there, add them together. You're not going to get a bigger polynomial in terms of degree if you're just adding and subtracting or scaling. So it will still be in the set. So this set is closed with respect to addition, subtraction, scalar, multiplication. What about multiplication? Well, we've got 2 times x plus 2 now multiplied. Okay, you can multiply into the brackets here. You get some polynomial here. But we're looking at these now with our mod m glasses on. So this degree 2 polynomial, we first have to reduce it by dividing by the polynomial m there. So we subtract some number of this from it. But wait a minute, we can make the calculations a bit easier by saying here we've got a 4. The 4 is the same as a 1, and the 6 is the same as a 0. So we've really just got x squared plus 2. And then we can subtract one lot of m. So we've got 2x plus 1 there. And we've got some terms that cancel. So we've got minus x, and 2 minus 1 is plus 1. And we could write that as plus 1 instead of minus 2. And there we go. So, okay. So we get x plus 1. So we started off with two polynomials of degree 1, multiplied them together, and you think that you got something of degree 2. But no, remember, we're dividing by this m. It's all mod m, so we get something that's, again, in the set. It's apparently x plus 1. And it looks a bit weird, maybe. We've got 2x plus 2 times 2x plus 1. And that's equal to x plus 1? Yeah. Just in the same sort of weirdness way that, like, 3 times 7 mod 10 is 1. Like 3 times 7 is 21 as integers, but when we mod it, then everything collapses. And that collapsing, if you do it in the right way, it's really symmetrical, and in fact, we get a field. So that's... but hopefully those two examples also tell you it's not just about fields, it's about actually nice calculations. You know, we can do things much nicer and easier when we don't have to deal with fractions. So that's the other part of the story. So, there's a theorem. Okay. Well, the theorem starts off by being, nice and sane, and saying this is a vector space of dimension whatever. Yeah, sure. Well, that's what I said before. That's what I wrote on the previous slide. That we can add, subtract, and do scalar multiplications, and we still get stuff that's in the field there. And dimension n, yep, because there are n coordinates and so forth. The next part of the theorem, I don't even know. Look, it has multiplicative structure. What does that mean? I mean, and how can you call that, a theorem? But anyway, what I'm trying to say here is that, yes, you can look at the vector space properties, but it's also interesting to look at the multiplication and division part of the side here. And there is stuff to say about it. So this theorem is sort of more like a sneak preview to a bigger theorem and a more bigger discussion, which we'll have right now. There's another theorem. It says, well, when is this a field? And it turns out that sometimes it is. Well, it's a field when all of the field axioms are satisfied, and you can then go and see that they all are, except for one. And that's where every element has an inverse except 0. When does that occur? Well, that's that statement there. Well, that occurs if and only if, if you have some element which is non-zero, it has GCD equal to 0 when we look at the GCD of it and the modulus, just like for integers. So we can reuse those ideas here to say, okay, when does every non-zero element of this set here have an inverse? Well, that's when the GCD of every one of those polynomials G has GCD 1 when compared to the modulus M. And what does that mean? Well, that means that M is not divisible by any of those smaller polynomials. Otherwise, the GCD would be bigger. In which case, it means that M is irreducible. It's a prime. Actually, I don't even need the quote marks, but it's irreducible and a prime. So we've got exactly the same sort of theorem as we started with. So remember, when we were starting with the simple case, that's for integers, we had that ZP is a field if and only if P is prime. And here we've got exactly the same thing. Prime and irreducible collapse down to mean the same thing. We've just got a bigger set of numbers, so to speak. We've got these polynomials mod some polynomial, and when is that a field? Well, that's when what we're modding out with, whether it's an integer or a bigger integer, so to speak, a polynomial, well, if they are prime or irreducible, in other words, then we've got a field, otherwise not. So beautiful. And look, I sort of didn't explain, I didn't quite explain from this step to this step, but it's just as simple to explain as for the integers using exactly the same arguments, because we've got pretty much everything works up to now with Bezout's property, Euclidean algorithm, and so forth. So here's an example. How do we actually, find out whether, if we are given some M, whether what we've got is a field or not? So here we're dealing with a binary polynomial of degree 4. So here we've got that P is equal to 2 and N is equal to 4. So if we take all the binary polynomials, infinitely many of them, but those there, and mod out by this polynomial M here, then we'll get the remainders, which are all the polynomials up to degree 3. So there are 2 to the power of 4 of them. There are 16 different remainders from 0, 1, x plus 1, and so forth, all the way up to x cubed plus x squared plus etc. So describe it. Okay, well, that's a bit of a loose task to do. But first, the first thing that we need to do is first show that M is irreducible. So if M is irreducible here, then that complicated looking stuff there, the F there, is a field from the theorem we just saw. So we first have to show that M is irreducible. Actually, that is, that's sometimes a considerable task. And in general, for big polynomials, it's an impossible task. Just like for big integers, it's really, really hard. You have to spend a lot of effort to show that some random big number is prime or not. In the same way for polynomials, of course, it's even harder. It's the same scale of hardness, though. So, but for small polynomials here of degree 4, it's pretty easy. There are 2 things that could happen if this were not true. If it were reducible, we could reduce it into smaller polynomials in 2 different ways. The first way is that we took this degree 4 polynomial and factorized it into 2 polynomials, one that had degree 1 and another that had degree 3. The other way is that we can factorize it into 2 polynomials of degree 2. So there are 2 cases to consider here, and only 2, which is nice. It doesn't get more complicated than that, but 2 cases. The first one is that we can factorize this polynomial into 2 polynomials where one of them has degree 1. So that means, if you scale it up, that we can find a linear factor of this polynomial, which by the factor theorem means that we can find a root of the polynomial. So let's go figure out whether this polynomial has roots. Now, that might fill you with dread and oh damn, that's not usually a fun thing to do. If we're used to real numbers or fractions or complex numbers, then it's a degree 4 polynomial. Okay, we can probably do it, but it's going to be a painful thing to do. But no. This is much easier and simpler because we're dealing with binary numbers. So instead of having infinitely many potential roots, we've got 2, because the only numbers we've got are 0 and 1. Hello. So all we need to do, ask each of those, hello, 0, are you a root of the polynomial? And hello, 1, are you a root of the polynomial? And there we go. And you chuck them in. So 0 to the power of 4 plus 0 plus 1 is 1. So m of 0 is 1. What about of 1? Well, 1 to the power of 4 plus 1, that's 3, but everything is binary here, so that's 1. That's also equal to 1. So in both cases, we have that 0 and 1. When you stuff them into the polynomial here, get 1. You don't get 0, so they're not roots. So m doesn't have any roots, therefore it doesn't have any linear factors, therefore we can't factorize it into smaller polynomials where one of them is linear. So that gets rid of the first case really quickly and easily. The second case, though, is where we might have that this polynomial factorizes into two polynomials of degree 2. So let's figure out whether that's possible. And the lovely standard way of doing this is to just write it out. Okay, let's say that we could write it in this way. So we've got the polynomial written as some degree 2 polynomial and some other degree 2 polynomial, where we're just writing them out in general, where we don't know what A, B, C, D, those coefficients are. And we want to try to reach a contradiction. And I love this. It's sort of a nice little puzzle, a very easy little puzzle. So what we're going to do is first expand these terms. Then you get a bit of a mess, but with a bit of, if you do this a couple of times, you'll see, there's a pattern to it. And so we've got some coefficients here. We've got this one, this one, this one, and this one. And all of this stuff here, this mess, is also equal to the original polynomial. So we can compare the terms. Like, for instance, the constant term, BD, has to be equal to 1. So BD is 1. And let's look at the top term, A plus C. That's got to be equal to 0 because we've got a little invisible plus 0 times x cubed up here. So that's equal to 0. So if we use those sort of observations, then we can see, well, okay, we can, for instance, see those two terms. We could also compare these two terms there. And in fact, if we do that, we get this is going to be 0, and this has to be equal to 1. Okay, great. And then you use those facts, you play around with it a little bit, a tiny little bit of trial and error. So it is a tiny little bit fun. Also because you know that you won't have to do a lot of trial and error before you get the answer. It's not a long or hard task. But then you get, okay, what about AD? So we've got that AD plus BC. That was equal to, well, that's the quadratic term there, so that's equal to 0. But of course, it's also equal to, well, we have that BD was equal to 1. So if we're dealing with binary numbers, which we've got here, that means that both B and D have to be equal to 1. And in particular, they're Oh, thank you so much. Thanks. It was, and someone else. Thanks. Yeah, cool. Yes, this was, whoops, I might go, this is unfortunately not OneNote. Not too bad. Yeah, cool. So 1, yeah. Beautiful. Yeah, this will work. Otherwise, I would have said, what's going on? And did my brain finally collapse here in the middle of the morning? So here we've got B and D. They're both equal to 1. So all of this stuff here, if we just substitute B and D with 1, we get that's equal to A plus C. But, and thank you very much, both of you, for pointing this out, this is equal to 0. We had observed before that this was 0. So we've got 1 is equal to 0. But that's not the case. That's a contradiction. We've broken mathematics, and on such a beautiful day. But no, of course we haven't broken mathematics. We just had the wrong assumption. We can't factorize the polynomial like that. Okay, great, because then we've ruled out both of these two cases. We can't factorize into some linear term times something else, or into quadratic terms multiplied together. In other words, we can't factorize m at all. Okay, great. Well, now we can use the theorem that we had before and say, okay, if we can't factorize it, it's irreducible, in other words, then by the theorem that we had, then this set here, all the binary polynomials modded out by this polynomial form a field, which means that we've got 16 polynomials there, all of those, the 0 polynomial and 15 non-zero polynomials, and apparently each of them has an inverse. So we can have polynomials that have inverses because, well, how do we say that? Well, we've got, if we have some polynomials f and g, if they multiply together to give the little polynomial 1, or just the number 1, then they're each other's inverse, just like normal. So, you know, if you're trying to think, oh, how can we take like 1 divided by some polynomial and get a polynomial? Well, again, just like for modular arithmetic, if you're dealing with, you know, what's the inverse of, let's say, 3 mod 7, well, that's 5. So we don't have to look at, oh, 1, how can we find an integer by taking 1 divided by 3, and that's like a fraction. No, no. In modular arithmetic, things collapse down in a nice way, and here we have 3 times 5 is 15, which is the same as 1 mod 7, and the same thing for polynomials. If you have 2 polynomials that multiply together to give 1, then they're each other's inverse. And in this case here, we've got that everything does have an inverse except for 0. So this is a field. In particular, all of those 15 polynomials, which I haven't written up but mentioned, they can find some companion, possibly themselves, that when you multiply them together, they give 1 when we're reducing by m here. So this is a lovely property, because now we can do addition, multiplication, subtraction, and also division for all of these things in that set there. And we don't have to worry about, maybe we can't divide or whatever. So we've done half of the example here. The other half is to describe this field, but I think we might do that after a 5-minute break. And yeah, enjoy. And good morning to you online, and hello to all of those of you who might be watching the recording here. I hope that you're doing beautifully as well, even this late and tired part of the term. Hey. Ah, yeah.
I get everything up to here. I'm not sure. So what does m being irreducible have to do with?
Ah, yeah. Thanks a lot. So here we're using this theorem here, that if we have that m is irreducible, yeah. So exactly right. And that theorem looks a little bit complicated, but it's really just it's really just a generalization of this more simple fact there. And I suppose, yeah, exactly right. So here, irreducible means prime. Whoops. So irreducible and prime. My pen is so the same for integers. For for numbers in ZP, well, actually in ZP, ZP polynomials and other stuff, if that makes sense. I hope that anyone reading this slide will understand what's going on there. Oh, thanks, Kenny. By the way, did that make sense? Or? Yeah, cool. Oh, thanks, Johan. Yes, Kenny, can you go back and explain? Oh, yes, definitely. And thanks heaps for asking, Kenny. That's yes. So here we had that these 2 polynomials multiplied together give us x squared plus 2. And since we're reducing everything mod m, we can subtract. Actually, I might actually do it like this. So this is congruent to something mod x squared plus 2x plus 1. So, and here I'm trying to reduce this number mod that number. So I have x squared plus 2 minus what I'm modding with. So x squared plus 2x plus 1. And that gives me, well, the x squareds disappear. Then we have minus x, and we have 2 minus 1, which is just 1. So minus 2x plus 1, which I can also write as plus 1 x plus, whoops, where did my pen go? Oh, just a bit of a delay. Here you go, plus 1. And that's how we, that's how we get that. Does that, awesome, yay, and thanks so much for asking, Kenny, cool. And hopefully anyone here might also be, No, everyone's just either attentive or sleeping or. Cool. Yeah, thanks heaps. Anyone else? Anyone else have any questions? And, yeah. And how are you all doing? Everyone online. I feel a little bit bad. It's been easier than I'd feared. It's trying to juggle both in-person and online components, but I'm actually really enjoying it. It's going well, except I feel a little bit bad that I haven't. Yay, awesome, Ahmed. Oh, that's really good to hear. Yeah, I haven't always been great at paying attention to the chat in my distracted enthusiasm. Oh, I'm sorry to hear it, Julia. Oh, that's terrible. Oh, yeah, that is one. Yeah. Hope it's not always been too bad, and also for you all. How's that affecting tests and stuff like that? Is that giving any bother? Ah, good. Awesome. And I hope that your morning is going great too. Ah, okay, yeah. I never quite know when it's a good internet bad or a bad internet day, whether that's got to do with traffic, user traffic, or the weather, or who knows. Coke, that's what I wanted. Where do we get to? Yes. Here we go. Cool. Okay. Yes. So so this example here was, and thank you, by the way, for your questions. They were excellent. And one thing to mention here, and thanks heaps, Kenny, for asking that. In these calculations here, some of these details I went through quickly, but if you want to think in terms of the integer modular stuff just to make it a bit easier to, you okay, to deal with the polynomial modular stuff, well, you can actually just deal with congruences. Like, so for instance, x squared plus 2 is congruent to this number here, mod that number there. If you're more used to that terminology, then that works fine. It actually makes perfect sense. And here we'd be saying, okay, take this number, subtract one lot of the modulus to get this. Okay, so they are the same, mod this number. And that's what we're doing with an equal sign there, because here everything is in the context of the mod that polynomial and mod 3. So, but anyway, I've written down a couple of more details there just in case you might be of interest to you. And what else was there to say? Yes, this theorem here, sorry, all of the polynomials divided out by, or modded out by m, form a field if and only if m is reducible, and that's exactly what this example is showing. So we're taking some, we're given some polynomial. Oh, thank you very much. What a lovely polynomial. So it's binary, and if we can show it's irreducible, then we have a field, because we take all the binary polynomials, modded out by that polynomial, and which we did here. We showed that it's irreducible, and that set there is therefore a field. And yeah, and the good part about that is that, well, we can multiply, add, subtract, multiply, and also divide by all numbers. In the case of division, not by 0, but otherwise by all the numbers being the polynomials, the 15 non-zero polynomials. So we also had to do something else in this example. We had to show that this polynomial was irreducible. Tick, we've done that. But also describe the field. Well, it's, oh, what a lovely field. It's sort of nice and, yeah, okay, great, done, tick. No, okay, I described a bit more. It had 16 elements in it, because we're dealing with binary numbers, and we've got that the degree here is n is equal to 4. So the size of, or the number of things in this set here is p to the power of n, or in other words, 2 to the power of 4 is equal to 16. And I hope that doesn't give you traumatic flashbacks from test 1, where you had to do some similar type of, actually exactly the same, it turns out. How many vectors are there in this in the, or how many code words are there in this code, if it's binary and has dimension, whatever. That's what we're doing there. But here it's sort of a little bit more formal, and we're not dealing with specific codes or whatever. So, okay, we can do more to explain it because, well, what's the structure of it? What's the structure of this set here, this field? Well, there are two answers. First of all, there's the addition and subtraction structure, which is just, well, look at the remainders there. There they are. They're all the polynomials of degree up to 3. And the coefficients are just binary, so zeros and ones. And we can find, 2 to the power 4 different ways of choosing A, B, C, and D. There are your polynomials. This forms a vector space. That just means that whenever you take 2 of those polynomials and add or subtract, you still get one of these polynomials. If you scale it up and down, hey, then you also get one of these polynomials. So there you go. That's from the addition and subtraction vector space perspective. But of course, we can do more than just add and subtract. We can multiply and divide. Now, how do we express that in some nice and easy way? Well, what we're going to do here is trying to find a primitive element, it turns out. Just like for integers, we can find primitive elements for this sort of thing here. And that's what we're going to do. But how do you find them? Well, trial and error and guesswork. Now, for you, that's okay. That's perfectly fine, because whenever you get something in the lectures, tutorials, tests, or exams, sorry, not plural, one is bad enough, but then trial and error won't take you very long. But in general, in the real life, where you're dealing with big vector spaces, then that is actually a really hard problem, and one that we don't have a really good solution to. So anyway, let's go see, can we find a primitive element? And if you've forgotten what that means, you'll find out very quickly from the example. But just to quickly say it, it's some number here, one of these polynomials, that if you take all the powers of it, x squared, in this case here, x, because that's going to be our first guess, then it generates all of the other polynomials except for 0. So we have to try to find something like that. Now, the way that we do that is to see, okay, we've got that x to the power of 4 plus x plus 1 is congruent to 0 when we're modding by that polynomial there. So that's just a trivial little observation, but it's a really useful observation because it means that x to the power of 4 plus x plus 1 is 0 if we use the other notation instead of using congruences or whatever. And that's exactly what we've written down there. Why is that useful? Well, that means that we've got this recursive calculation property whenever we have x to the power 4, or here I'm calling it alpha because primitive elements we often call alpha, beta, gamma, or whatever. Hopefully alpha, because that's our first guess. Our second guess, if alpha didn't work, would be beta. And if you get to gamma, you start to get annoyed. But alpha is nice and happy. Let's hope that this works. Alpha to the power 4 is equal to, well, minus alpha minus 1. And here, if what's this alpha business? Well, that's just this is our first guess x. I'm calling it something different, but anyway, all of these are binary things. So this is really just alpha plus 1, and we could have also written it as x plus 1, but we're sticking with the alphas. Okay, so we've got that tiny little recursive property, and that's really useful because whenever you have some polynomial which is big, we can collapse it down using this recursive property. So if we have the degrees get to be 4 or bigger, we can slam them down by making this substitution. So let's see how this works. So any power alpha to the power of k, even if k is like 1 billion, we can just keep using this recursive property to chip away at the degree until it's under 4. It's under 3. Oh, sorry, 3 or less. In other words, it's a polynomial of this type. So let's. There are a couple of more stray comments in the description, which was beautifully vague. Yes, yes, Luke. No, exactly right. Exactly right. And that's a really good point. Here, when we're looking at multiplication and division, we carefully say, sorry, 0, we love you, but not today. I mean, yes, we still love you today, but you can't play with us, sorry. Yeah, it's a bit cruel, but yeah, it is a bit cruel. Anyway, so so there are a couple of more things. Okay, we can talk about it as a vector space, whatever. So let's test out whether this could actually, this guess here, x that we're calling alpha, could be a primitive element. Now, the reason that I want to do that is exactly the same as for the integers. Primitive elements are awesome in the, well, for theoretical purpose, but also really practical purposes, because if we want to describe this set from a multiplicative or a division perspective, what we really want is a multiplication table. But in this case, that's not too bad. It's a 16 times 16 multiplication table. Sorry, a 15 if we exclude 0. Okay, 14 because 1 is a bit trivial too. 1 times anything is. But still, it's a big table. If we can find a primitive element, then we can make a very small table just with 15 elements in it that are all the powers of that primitive element. And then we can use those powers to do multiplication really easily, just like we did for integers. So that's why we're looking at this. But first of all, we have to find a primitive element. So our first guess is to say, okay, try to find the simplest guess possible. It can't be a constant like 0 or 1 because the powers of them are not going to be bigger polynomials. But what about x? Could that be a primitive element? Okay, let's go see. So we've got alpha, or in other words, x. Alpha to the power 1 is just alpha, 2 and 3. There's nothing really interesting going on here. But what about, what about alpha to the power 4? Well, that was alpha to the power 1 by this recursive identity. So alpha to the power 5 is alpha squared plus alpha. Alpha to the power of 6 is alpha to the power 3 plus alpha squared. And it's getting a bit boring now, but that's okay. At least it's okay for me. I don't know about you, but... sorry? Alpha squared. Oh, thank you. Oh, thank you very much. Yeah. Otherwise, things would be very easy and also wrong. And here we go. Alpha to the power 4 plus alpha to the power 3. That we can collapse because alpha to the power 4 was equal to alpha plus 1 plus alpha to the power 3, which we can rewrite a little nicer as alpha to the power 3 plus alpha plus 1. I love doing this. It's sort of meditative. Maybe not so meditative for you watching it, but anyway. Alpha to the power of 8 is, well, just what we had before times alpha. Alpha to the power 4 plus alpha squared plus 1. Again, we can do the substitution. Alpha plus 1 plus, thank you. Okay, that was a very bad fix. Thanks heaps. I might just, no. Okay, I'll go back. Thanks. Yeah, alpha plus 1 plus alpha squared plus alpha, and everything is binary here. See ya, and have a lovely weekend. And so here we've just got alpha plus alpha, so in other words, 2 alphas, or 2 x's if you want. So these cancel out because 2 is 0. So that's the same as alpha squared plus 1. Okay, onwards, alpha to the power of 9. And so far, one thing that I'd like to point out is that all of these powers are different. So we haven't got back to anything that we've got before. So this is going pretty well. And if you think about it a little bit more with some group theory in mind, well, the powers of alpha here are going to, or x, are going to form a subgroup of the whole set of units of these things that were here. The units is everything except 0. There are 15 of them. So by Lagrange's theorem, the subgroup of these powers has to, the number of things in that subgroup, the powers of alpha here, has to divide 15. So we've either got 1, 3, 5, or 15. And actually, when we got to 5 here, we could say, no, that's not equal to 1. So apparently alpha is a primitive element. And then we could stop and say, yeah, we found one. But if we didn't know that, or if we wanted to actually know the powers of alpha, because that's actually useful, then we can go on. And if none of that made sense to you, then don't worry. You might pick it up or you might not. It doesn't really matter, but it's a nice little shortcut if you do. Anyway, so let's go on. We're almost there. Alpha to the power of 10. Here we've got another alpha to the power of 4. And thank you very much for correcting my previous errors. I hope that this is still error-free. When you're doing this, and I think it's a good idea to do, I think there is a question in the practice test, test 3, where you are invited to do stuff like this. Even though writing out the table like that is a lot of work, possibly, if you feel that it is a lot of work, it's worth doing, because the rest of the, a big chunk of the question is about this. And as we'll see in the tutorial problems next week, will we? Is it next week? Yeah. We'll also see that it's a good idea to first make the table. And even though it's a lot of work, it's sort of nice and easy and sort of meditative. I sort of like doing it. But also, there's inherent error correction inbuilt in it, because right at the end, when we get to alpha to the power of 15, which I hope that I can fit on the page somewhere here, we'll get 1. If you don't get 1, you've made an error, and then you can look at where the error might have been. Anyway, let's go on with this. Alpha to the power of 11 is straightforward. Alpha to the power of 12, we're almost there. Alpha to the power of 4 plus alpha to the power of 3 plus alpha squared. And I'll just have a little shortcut here. That's alpha to the power of 3 plus alpha squared plus alpha plus 1. Where do I? Okay, sorry about the mess here. Alpha to the power of 13 is equal to alpha to the power of 4 plus 3 plus 2 plus 1. And that's equal to, and here I'm just going to skip one step. And alpha to the power of 14 is alpha to the power of 4 plus alpha to the power of 3 plus alpha, and that gives us alpha to the power of 3 plus 1. And alpha to the power of 15 is alpha to the power of 4 plus alpha, which is in fact equal to 1. Yay! So almost certainly we've done it correctly, because it's pretty unlikely that you get 1 at the end if you don't. So awesome. Okay. So why did I do that? Well, just to remind you again, this was for one thing to say our first guess, what could be a primitive element, alpha equal to x. That actually worked. We have a primitive element. Secondly, yay, we have a primitive element, because now we can express all calculations, all the multiplications of any two of these elements in the field here as powers of, or multiplication in terms of the powers of alpha, which is just is just addition, mod 15. And I'll show you how that works too. So anyway, let's calculate the powers of alpha, and we've done that there. Here they are written up nicely. But anyway, so alpha generates the units of the fields, in other words, the non-zero elements. Yeah. Exactly right, yeah. So 16, and we get rid of, 0, and 15. Yeah, cool. It's a primitive element, and so forth and so on. And that means that we can express all of the non-zero elements of the fields, the units of the field, as powers of alpha. So 1 alpha to the power of 2, all the way up to alpha to the power of 14. Or we could have started with alpha and gone up to alpha to the power of 15, which is 1, doesn't matter. And of course, we also have 0, which is not a power of alpha, but we have to include it when we're talking about the whole field. So arithmetic is very easy using this table of alpha powers I claim, and that's what I claimed before. And behold, look at how lovely it is. So if we take these two polynomials there, and here alpha is really x, so some cubic polynomial x cubed plus plus x plus 1, if you want to think in terms of x, times alpha cubed plus x squared plus 1. Well, that gives you some unholy mess, like if you're to expand it. But don't worry, we don't have to do that mess, because we can use the table. We just say, where do we have alpha cubed plus alpha plus 1? Which power is that, would you say? Yeah. It's alpha to the power of 7. It's I was going to draw on the wrong screen here. Here we go. This is alpha to the power of 7. And what about this polynomial here? Which polynomial is that in the table? Awesome, 13. Yeah, exactly right. And please feel free to also answer online if you feel like it, but only if you feel like it. And there we go. Alpha to the power of 7 times alpha to the power of 13. Simple. That's alpha to the power of 20. Well, we don't really have alpha to the power of 20 in the table, but we do have something that can reduce that 20. Alpha to the power of 15 is 1. So we can get rid of 15 of the 20 alphas there, and just give us alpha to the power of 5. Yay! And that's a beautiful, simple answer that we could just say, okay, that's fine. But we could also go back to the table and say, that's the same as alpha squared plus alpha. And there we've got that expression too. And there you go. So arithmetic using the table is really simple and easy. I hope that you can see there as well. So what about division? So we can do multiplication and division using this table. Division, well, alpha squared plus 1. Can you see what alpha squared plus 1 is equal to in the table? Awesome. Yay. It's alpha to the power of 8. So alpha to the power of 8 minus 8, well, what's that? Well, again, we can use that alpha to the power of 15 is 1, so we can multiply 1 here by 1 there, or in other words, multiply by alpha to the power of 15, and then we get that that's equal to alpha to the power of 7, which is a fine result, but if you want it in terms of small polynomials, then you can use the table once again and get alpha to the power of 3 plus alpha plus 1. And hopefully you can see that this is beautifully elegant and useful, and this is why we use it in so many areas for cryptography, for error correction, for pretty much everything, in terms of communication, if you're dealing with just slightly bigger fields. So, yeah. Any questions about all of this so far? And let's see where we got to. It's very easy. Let's have another example. So, actually, damn. Let's have a slight interlude. This is the grand theorem that explains everything that we need to know in terms of what a finite field is and what properties there are. And it's a beautiful theorem. It's a bit hard to prove, and we don't need to prove it, so we won't prove it in this course, which is a pity because it would actually be nice to understand why it's true, but that's not, that doesn't quite fit the purpose of this course. The finite field theorem, very large, and bold, capital lettered named theorem because it's a really central theorem. And look at what it says. If you have a finite field, then that finite field has exactly this many elements. It's got a prime power number of elements. There aren't any finite fields that have some other type of number of elements. Another thing is that if you do have a prime power, then there is a finite field with that number of elements, and there's exactly one. And in fact, the deeper understanding of all of this, the deeper Coke. Where's my word? The deeper underlying reasons for this is that, well, the only type of finite field that we have is the one that we've already seen. You take some polynomial, you divide out by an irreducible polynomial, and what you get is a finite field. Now, finite fields, you can dress them up in whatever way you want, but they essentially just this type of field, and that's it. So if you have infinite fields, they come in all sorts of weird and wonderful flavors, but finite fields are extremely elegant and beautiful, uniquely described. Of course, that's not quite true. If you look at them in detail, then the binary field looks very, very different in its multiplicative structure than the ternary one, which looks very different than the one, the field of size 4 and 5 and 7 and 9 and so forth. Each of their multiplicative structures are actually weird and wonderfully varied. But if you just look at how many elements are in them, then everything is very simple. If you talk about how to construct them, or if you up to isomorphism want to represent them, then everything is also brilliantly and beautifully simple to describe. And that's described on the rest of the theorem, which is here. A whole, okay, look. Yeah, okay, so it's a bit more complicated than just the first bit. Look, the first bit is elegant. The second bit, all of that stuff there, basically says what we've already been saying. So if you talk about these fields in terms of addition and subtraction and scalar whatever, then we're really just talking vector spaces. If we're talking multiplication and division, then we're really just talking about taking some primitive element, and some primitive element will always exist. We haven't proven that, but it's true. And then we can express multiplication and division in terms of that primitive element, the powers of it. Also, how many are there? How many primitive elements are there? Well, that's exactly the same as what we saw in the integer case back when we started the chapter, but it looks a little different now. The number of do we see that here? No, I'm thinking excitedly about some theorem that we'll get to. But anyway, yes, Luke.
I forgot what isomorphism means.
Isomorphism means just you can. So something is isomorphic to that if they look different, but actually they've got the same shape, even though they have been dressed differently. My first example that springs to mind, because I love combinatorics and graph theory, is if you have some graph and redraw it, you've got the same graph, but they are or you relabel, you've got the same structure. So iso means the same, and morphism or morph means shape. So same shaped. So in topology, you'd talk about a donut and a cup. They would be isomorphic from that perspective.
Okay, so for like your previous roots, your table, each element of the table showed two isomorphic things.
Actually, that's a beautiful example. Yeah, if we chose two different, if we found two different, my brain just died. Ah, hey brain. Sort of. Yeah, off and on again. And doesn't it always, you bash it a couple of times and it works, but that might not work here. Primitive elements, there it was, yeah. So if we found two different primitive elements and made two different tables, we'd be expressing all of the elements of the field in two different ways, but we'd be expressing the field essentially. We'd say here's the structure from this point of view, here's the structure from this point of view. So it's the same structure, just seen from two different angles. Yeah.
I've noticed that you've made a pretty big deal of the fact that the polynomial is irreducible.
Yeah.
Can you just possibly reiterate why that is?
Definitely. So if we go back to the integer case and see, okay, let's look at things mod 12 or something like that. So some number that's not irreducible. In other words, it can be factorized. Then we can find numbers. For instance, let's say 4. Actually, let's make it a little bit more interesting. 8. 8 inverse. Well, there is no inverse. And the reason for that is that 8 and 12 have a factor in common, like 4, for instance. So every multiple of 8 is going to be a multiple of 4, and therefore we're saying 0, 4, 8, 12. We're back to 0 again, without having gone through all of the other ones. In particular, we haven't got to 1. And the same thing is true for polynomials. If we have some polynomial, and here, whoops, here if I there you go. Yay! If we have some polynomial m that's not irreducible, then we can write it as f times g for smaller polynomials. And there, for instance, f inverse won't exist, because if you look at multiples of f, then we'll get back to 0 at some point before we've got to all of the others, including 1. So yeah, awesome question, and thanks so much. I've sort of just been alluding to, we do the same things as for the integers, but I haven't actually made the connection explicit. So thanks heaps for letting us do that. Was someone else had a question somewhere? Cool. Yeah, awesome. Yes, so here we have an example, another example. Show that this polynomial here is irreducible. Now it's a ternary example. So the degree is smaller, but the number p is slightly bigger. So construct GF, by the way. And what's that? Well, that's just another. Yeah. If you look at this, all the details of this messy slide here, you say, well, how do we actually write up this field there? Well, there are different ways of writing it up. I'm sort of used to writing it as f subscript q, where q is the size of the field, like p to the power of n. Other people are more interested in writing gf of q. That's the Galois field, could go into a historical side note about Galois and whatever. But for those of you who are used to calling it g of f of q, keep doing that if you want. But we've got different ways of writing up this notation, and that's all there's to it. We're not going to talk about Galois fields or whatever. So we just have to construct this field. So in other words, this is the field. You take the ternary numbers and you use them to find all the ternary polynomials. So these are the coefficients of the ternary polynomials, and then you mod out. By m, this little polynomial, which we have implicitly, which we're told is irreducible, or we have to show that it is. So this is the field that we have to construct. And by construct, we have to show, well, what does it do? What are the elements? And how do they work with addition and subtraction? And how do they work with multiplication and division? So we've got to do two things, but let's just make it clear. Here we've got that p is equal to 3. and here we've got that n is equal to 2. So the size of this field, and here I'd say, and here use another notation, f. The size of this field f is equal to p to the power of n, so that's equal to 3 to the power of 2, which is 9. And in fact, this is the same example that we saw earlier when we're looking at remainders, and there were 9 of them. But anyway, so show that this little polynomial is irreducible over the ternary numbers. Well, since it's only got degree 2, there's only one way in which we could factorize it in terms of smaller polynomials. That's if we factorize in terms of a degree 1 polynomial times another degree 1 polynomial. If you can do that, well, then you've factorized it into a degree 1 polynomial, and therefore you can find a root of the polynomial. So if we can show that that polynomial doesn't have any roots, then we're done. And that's all we need to do. And again, this is really easy. You don't need to, take some quadratic equation and whatever and find the roots of that. No, we've got 3 roots that could be roots, or rather 3 numbers that could be roots: 0, 1, and 2. The ternary numbers, only 3 things. So we can just check whether they are roots. So plug into this expression here. 0 plus 1, that's 1. No, that's not a root. What about 1 and 2? Well, if we have 1 squared plus 1, in the binary case that was 0, but in the ternary case that's equal to 2, which is not 0. So what about 2? Well, you have 2 here. That's the same, by the way, as minus 1. But 2 squared, if we just stick with 2, plus 1 is equal to 5, which is equal to 3. 2, sorry. That would be bad if it were 3, because that would be 0, but this is non-zero, so we can very, very quickly check whether each of these 3 numbers are roots, and they're not, so therefore it doesn't have any roots, therefore it doesn't have any linear factors, therefore it's irreducible, because it's such a small degree. Yay, we're done. Now construct the field. Okay, well, for one thing, in terms of addition and subtraction, we just look at what we've got. They're the remainders. Ax plus b, they're the type of remainders that we get when we take the ternary polynomials and divide by this quadratic polynomial. So there are 9 of them, and we can add and subtract in the usual way, just using ternary, like mod 3 when we're dealing with the coefficients. But when we want to deal with the multiplicative structure and describe that, then it would be good to either write out a multiplication table, but there are 9 elements here, so it would be 9 times 9, and that's not too bad, but it would be better and also more user-friendly if we can find a primitive element to represent these multiplication tables and also to use them. So we want to find a primitive element. So we could start off by trying to find test the very simplest example that we can find, like x. So the constant terms, they wouldn't, if you take 0, 1, or 2 and take powers of them, you're not going to get like x squared or whatever. But what about x? Well, alpha equal to x, well, we've got this recursive property now, because now we've got that x squared plus 1, well, is 0 mod itself. So that gives us alpha instead of x plus 1 is 0. Or in other words, we've got that alpha squared is equal to minus 1. And since we're dealing with ternary terms, alpha squared is equal to 2. Okay, well, what happens when we look at the powers of alpha? We get alpha to the power of 0 is 1, alpha to the power of 1 is alpha squared is 2. But this is not going to go very well, because, okay, alpha to the power of 3 is 2 times alpha, great. Alpha to the power of 4 is 2 times alpha squared now. But when we substitute alpha squared by 2, we have 2 times 2, that's 4, or in other words, 1 mod 3. Okay, damn, that's not good, because now we're back to 1. So if we have 9 elements, one of them is 0. Sorry, 0, you can't play with us just for a second. We're going to be the units over here. There are 8 of them, and we want to find the 8 units as powers of alpha there. Well, that's not going to work. We only have 4 powers that are different. Alpha 1, alpha squared, alpha cubed, and then we start recycling or cycling around and around. We're not going to get the other one. So this guess did not work. So our little trial and error process will have to continue with a different guess. Okay, well, what could we guess that would be almost as simple as x? Well, what about x plus 1? Okay, damn, alpha was not primitive, but let's see. So let's try instead with something also pretty simple, like gamma. So gamma equal to alpha plus 1 or x plus 1. Let's see. gamma to the power of, that's not alpha. Gamma, so gamma to the power of 1 is 1, gamma to the power of 2 is, sorry, that's, yeah, thanks. Which is alpha plus 1, gamma to the power of 2 is alpha plus 1 squared, which is alpha squared plus 2 times alpha plus 1, which is, and then now we can use this, that alpha squared is equal to 2. So that's equal to 2 alpha plus 2 plus 1. They cancel out because that's 3, which is 0. So that just gives us 2 alpha. Okay. Alpha cubed, that's equal to, 2 alpha times gamma, which is alpha plus 1. And there are other ways of doing this, by the way, but this is just one straightforward way of doing it. So we get alpha 2 alpha squared plus 2 times alpha, which, and we've already known that 2 alpha squared is equal to 4, or in other words 1. So we've got 2 alpha plus 1. This is looking good. Now the crucial point, I suppose, is this one here, alpha to the power of 4, because if that's equal to 1, then we're stuffed. But if it's not equal to 1, then again, by those comments I made about Lagrange's theorem and subgroup sizes dividing others, well, there are 8 units, so the number of powers that we have of gamma here would either be 1, 2, 4, or 8. And if, they're definitely not 1 because we've got more than 1 power. They're not 2, but are they 4? Well, let's have a look. So here we've got 2 times alpha plus 1, then times alpha plus 1, and that gives us 2 times alpha squared plus 2 times, what was that? That was supposed to be handwriting, actual writing. And then we go, these cancel out, and this is equal to 1, so this gives us 2. Yay! Awesome! Because 2 is not 1. So anything that's not 1 is good. Okay, great. And also, 2 is minus 1. So we actually calculated correctly, presumably, because when we look at the very last power that we'll have, gamma to the power of 8, that's got to be 1. So the halfway point should be minus 1 if we want to take the square of it. So it looks as if we've done the calculations correctly, and then you can continue them, and you get the table here. And in fact, yeah, we have a primitive element, and I'm not wasting your time pointlessly with having to do another trial here. So yes, we have a primitive element, and it's and the powers of gamma there are expressed in terms of the alphas there, which alpha was just x. So these are the little polynomials that we're dealing with, just in slight disguise. Yeah. Yeah, really good question. Will the primitive element always be something simple like x or x plus 1 or whatever? In real life, no. But in this course, yes. Yeah. It would be cruel and inhumane to get you just to do a whole lot of trial and error, and like you'd never get a quadratic term, by this. That would just be so evil. Yeah, I don't know. It's it depends a bit on the type of question that you might get in a test or exam or tutorial problem, whether it's just the first guess or it's the second guess. In the extreme case, it might be a third guess. Like it could have been like, instead of gamma alpha plus 1, it could have been alpha plus 2. But this is a relatively rare case. Yes.
The nice one here is that we have gamma 8 plus 8 those easily by switching the sign. So you can have gamma 5 equal to negative alpha minus 1, which is 2 alpha plus 2.
Yeah. So actually, that leads on to another beautiful line of thought. Sometimes, if you do have a primitive element and you've done some of the calculations here, maybe you can go backwards as well, or sort of by flipping the sign. And another thing is, if you have found one primitive element, then you can find all of them actually in the same way as for integers. Yeah, there are a couple of little shortcuts here and there when you're doing these things, but yep. Yeah, no, great.
Could you, like, in terms of how we get to your primitive to be alpha plus 1,
Yep.
could you pretty much tell from the get-go that it wasn't just going to be x equals alpha because the x squared plus 1 was made
Yeah. Here I'd sort of, there is a little bit of, oh damn, what happened there? Just a second. Now I have a scary looking screen. Oh no. There was all sorts of weird. Oh, okay, now it's back to what it was. Restart required. No. Oh, damn. What's going on here? My laptop seems to have stuffed itself. Huh. That's just a second. Oh, okay. That's one thing that this. I wonder whether it's got to do with the battery. I'll just see whether the. Yeah. Oh. Let's see. Let's see. Huh.
Then you're going to end up with the Z5 ring.
Yeah. I wonder whether that. I might take it on this one then. Let's see. For some reason, this charger isn't actually doing any charging. Yeah. Oh, hey, it's working again for some reason. Okay. Okay, while it's working, I'll use it. Yeah. But I do want to get through a couple of things. Anyway, okay, it's working for now. So, okay. Yeah. And damn, what's going on here? Yeah. Okay. It's acting really weird, but anyway, let's see. Okay, I'll continue as far as this seems to work. Yeah. Okay. Cool. Yes. So we can use both the powers of gamma and alpha to make these to do arithmetic operations even better than if we just had one table. So look at this, for instance. If you want to express your field elements in terms of gamma, and you've got some calculations going on here, gamma to the power of 2 plus gamma to the power of 3 divided by gamma plus gamma to the power of 7. That looks really complicated, especially if you remember that gamma here was x plus 1. So, if we wanted to expand x plus 1 to the power of 7, add x plus 1 and divide that into the top stuff. No, but now we've got the beautiful, helpful and small table here. So gamma to the power of 2 and gamma to the power of 3. Well, there you've got 2. I almost don't dare touch the laptop now, but there we go. That's the top part. The bottom part you recognize, well, that's alpha plus 1 and gamma to the power of 7. If you look at the table, that's alpha plus 2. And since we're dealing with ternary numbers, then, for instance, 2 and 1 disappear, and we've got 2 times alpha down at the bottom. And here we've got 2 alpha and 2 alpha. That's just alpha. So that collapses. And, okay, we're not done yet. Then we can say, okay, let's use the table again. 2 times alpha, where is that? Actually, where is that? So 2 times alpha, how many powers of gamma do we have? Yay, exactly right. Yeah, that's that one there. And I suppose alpha plus 1, that was just gamma to the power of 1. So we've actually just got gamma divided by gamma squared. So that's gamma to the power of minus 1. And then we can use gamma to the power of 8 to turn that into so times 1, or in other words, times gamma to the power of 8 into gamma to the power of 7, which is beautifully simple. But if you wanted to express it in terms of some alphas, then you can say, well, what's that equal to? Yeah, exactly right. Alpha plus 2, and yeah, and there we're done. And we did that scary-looking calculation in just one line, just by using the table a couple of times. So backwards and forwards between the gammas and alphas, and then using some modular arithmetic like mod 3 to cancel things out and simplify and so forth. So this theorem here is exactly the same sort of theorem as what we saw for the integers, talking about Well, when do we have a primitive element? Well, in this case, always. So if we're dealing with a finite field, there's always going to be a primitive element, which is lucky. We haven't proved it. We're not going to prove it, but it's true. And that means that we can write up the multiplication tables in this really nice and user-friendly way. Also, how many primitive elements are there? Well, first of all, if you have one primitive element, and there's always going to be one now in the field, there are any other power of that primitive element, beta to the power of k, is primitive if and only if the GCD of k and the number of units there, which is q minus 1, is 1, because they form a, each of the elements of the field correspond to one of the powers of the primitive element. So instead of looking at the elements of the field, we can just look at the indices, like 1, 2, 3, all the way up to cube. So gamma to the power of 3 instead of alpha to the power 2 alpha plus 1. We can just look at the 3, that number 3. And when we're doing multiplication, we're just adding those numbers together, mod the number of units, which is q minus 1. So the number of primitive elements is just the number of units mod 15 in this, 8 in this example, but more generally q. So I'll just point that out. This is the number of units. And I'm pointing this out also for another reason. I think there's a test question about this sort of stuff that comes in sort of two variations, if I remember correctly. One where we're dealing with a field, and one where we're dealing with Zm, where m is not necessarily prime. And there we had the similar theorem just back in one of the first lectures of. So here, if you remember, we had phi of m. That was the number of primitive elements back then. Well, that's because phi of m, that was the number of units. So we're doing the same thing here, except that now we've got phi of q minus 1, because that's the number of units now. So here we've got in Zm. Anyway. And yes, we've just got a little bit more time, so let's begin on the final concept of this part of the chapter, which is about how to actually construct these fields. Now, we sort of know that already. All we need to do is go out and find an irreducible polynomial. But how do you do that? Like, they are like prime polynomials. And finding prime numbers is hard, let alone prime polynomials. But what we can do, if we are given a little bit of help, is try to construct one given one of the elements that we've got. In particular, if we have a primitive element, then we can find a polynomial which will do the trick. It's sort of a bit circular, this argument, but let's have a look. First, we have a theorem, and by the way, this is if you remember Fermat's theorem, that was upgraded by Euler's theorem. In a way, this is sort of upgrading again. Or maybe I shouldn't say quite upgrading, but this is a more general field version of Euler and Fermat's theorem. So we've got some element to the power of the size of the field, p to the power of m, n, and that's equal to a. Now the reason that that's interesting is that if you have the polynomial x to the power of p to the power of n, well, and you subtract x, that polynomial there, let's call that some m, capital M polynomial. Well, that means that every element of the field there satisfies this here. Ma is 0. That means that every element of the field is a root of this particular polynomial that we've written up here. So why is that interesting? Well, if you look at that big polynomial, it has every one of these elements as a root. So if you look at some particular element a, it's a root of that polynomial, but could it be a root of something smaller? And in fact, if we look at the smallest polynomial, or a smallest polynomial, it happens to be irreducible, and there you found an irreducible polynomial. So that's the sort of very vague approach that we're going to look at. We're going to say, okay, take some element of the field, and we're going to actually construct the field from that element in the field. So it's a bit circular, but if you can start off somewhere with an element of the field, you can say, okay, it's a root of that polynomial, but could it be something smaller, some smaller polynomial that is also a root of? And that's what we're going to do. First to say that such exists and it's unique, and then to say how do we actually find it? And how do we find that in 2 minutes? I'm not sure that we'll be able to do it, but we'll be able to talk about that on Tuesday and finish that up. By the way, on Tuesday, we'll be finishing up all of this stuff here and going on to the last part of chapter 5, which is about how to test for when a number like an integer is prime. That's actually pretty interesting stuff. We'll go through it fairly quickly. There's not a lot to learn there. And then we'll also be talking about random numbers, how to generate deterministically a random number, which makes no sense, but how you can sort of do it somehow anyway, pseudo-deterministically, or sorry, pseudo-randomly. And that'll be the end of chapter 5. And yeah, so we'll finish that on Tuesday and start on chapter 6. But and in the tutorials, there'll be 2 tutorials next week, by the way. There's the usual tutorial, and then there'll be a bonus tutorial on Friday at 2 online, just to cover all of the chapter 5 stuff in the tutorial, so that yeah, by midway, roughly midway, possibly in Tuesday's lecture, we'll have finished all of the chapter 5 stuff that you need for the test, and by the end of the week, we'll have covered everything in the tutorials that you need for the test, and then you'll be set for week 10. Anyway, just to say one more comment, we've got a definition, and I would like to just explain the definition and leave it at that, but so that we have some recollection of this stuff when we meet again, which I look forward to doing. Yay! I can look forward to that all weekend. But now the minimal polynomial here, it's if you do have an element of the field here, then there is a unique monic polynomial which has this element as a root, and it's got smallest degree. So this is the thing that we're going to be talking about next for a little bit, and that'll be the end of this finite field chapter, and so forth and so on. I think that's about it for today. If you have any questions about anything, please feel free to come up and chat. Otherwise, have a beautiful weekend, and thanks for a happy, if slightly rushed, hopefully not too rushed lecture. Thanks heaps for your questions, and yay! Yeah, thank you, and oh, thanks Xiao Yan and Liam. Yay! Thanks Julia, and oh, thanks Jasper, and yeah, thanks Gabriella. And thank you, Luke, for your awesome questions.
I was just happy I could get A's, and you said of the finite maths textbook, because
oh yeah, yeah.
It's like, you know, usually you don't get to do that.
Yeah, yeah. Oh, that's a fine-looking book too. Nice. Oh, actually, who's the author?
This was the Lindsay and Child.